Right, shall we start? I mean, this, what I was talking about was very practical application of knock-related things and how fuels and engines interact in terms of knock. But now we'll go a little bit deeper into the fundamentals of auto ignition and knock in engines. Okay. First thing you have to remember is knock, like any other engine, operating parameter, is a very stochastic phenomenon. I mean, for example, we in all the things that I said before, we're just assuming the fuel and air is pre-mixed and there's just, auto ignition occurs and everything happens at once, etc. But that is not the case. Though the fuel and air are fully pre-mixed in spark ignition engines, the end gas is not, sorry, what happened here? Okay. The end gas is not homogeneous, because what happens in engines, where fresh charge comes in, there's hot gases inside the cylinder, they mix, and there's turbulent mixing. And there are always hot spots. Okay? And auto ignition always occurs in hot spots. So it's a localized phenomenon in whether it's a spark ignition engine or an HCCI engine. Okay? And combustion and knock are marked by cycle-to-cycle variations, because in a spark ignition engine, if you looked at, say, 100 cycles, there's a huge difference between the pressure developments. I mean, I'll show you some examples, for example. Because why is that? Because turbulent flame development is stochastic. So every time the spark fires, how the flame develops is not the same exactly. So the pressure development is very different. So the pressure and temperature changes in the end gas are stochastic. Even if you have running the engine at exactly the same condition, every cycle will be different. Okay? And most knock studies focus on knock onset. I mean, this is what we're talking about. When knock, at what crank angle knock occurs, for example. Where auto ignition is deemed to occur. That's what we are interested in. But knock intensity, how the pressure develops, pressure fluctuations develop after this onset of knock, after auto ignition, is determined by the evolution of the pressure wave set off by the knock onset. And the other thing that you have to remember is the primary operating principle in spark ignition engine is to avoid knock. You always try to run the engine where knock doesn't occur. However, in modern boosted engines, extremely high intensity knock, which is known as super knock, can suddenly occur sometimes, even though you're taking every care not to run the engine in your knock limits. Okay? And why is this happening? This is happening because there's another stochastic phenomenon, very unpredictable phenomenon, called pre-ignition occurs. And pre-ignition basically increases the pressure in the end gas compared to the normal operating condition. And if auto ignition occurs at these high pressures and temperatures, you can have extremely intense knock. But there is a framework which I'll discuss under which you can study all this. Okay? But it's important to realize that especially super knock has to be described in probabilistic terms. I mean, it's not every cycle is different. I mean, it happens randomly. So you have to understand that this whole process is probabilistic and rather stochastic. And many measures used to describe knock, for example, as I said already, are not truly objective. It depends on what assumptions you make and what your your measurement system is like. You can call anything that you want knock, for example. So there are a lot of subjective judgments you have to bring in. So all these things you have to remember. But still, that allows us to come to some kind of, make informed judgments. Now, I want to now relate what we talked about earlier to more fundamental matters, for example. That is to do with ignition delay. And what you have to remember is ignition delay and auto ignition depend both on pressure as well as on temperature. Quite often in chemical kinetics, I mean, of course, people know that it depends on pressure, but the focus is always on temperature. I mean, when we talk about the NTC region and so on, you know. For example, here is the actual data for isooctane, right? At different pressures and different temperatures. This is from a 1997 paper, for example. Now, you can see that as the pressure increases, you come down from there, and the ignition delay for a given temperature decreases very significantly. The auto ignition becomes much more likely. And similarly, of course, as the temperature increases, that means we are going this way here because it's 1000 over T, ignition delay decreases. We know this. I mean, this is what should happen. Now, it is possible to write ignition delay as tau naught times some function of very complicated function of temperature and a pressure dependent term, where tau naught is the ignition delay measured at any given temperature here, one given temperature, and one at P naught. So as you increase the pressure, ignition delay comes down. So in this case, this data can be collapsed like this, if you use n of 1.5 in this case, and the important thing is, this is for isooctane. If you do, people have done this, these kinds of experiments for N-heptane. And for N-heptane, N is around 1.65, 1.64 like this. But we have also measured this kind of thing for many different types of fuels. I mean, gasolines and mixtures of toluene heptane mixtures. And, the ones I was telling you were much more like surrogates, which are much more like gasolines. When you do that, the N value is not 1.5 or 1.6. Is around 1 or less. That's what you find in shock tubes experiment. So what does this mean? It means that if you have two primary reference fuel, which is the isooctane heptane mixture, and you compare it at the same temperature as this gasoline, for instance, with the N of 1, and you double the pressure. It's the same temperature, you double the pressure. For the PRF mixture, the ignition delay will come down by, say, 2 raised to 1.5. Okay? Whereas for the gasoline, it will come down by a factor of 2, just 2 raised to 1, say, if n is equal to 1. That means for the gasoline, increasing pressure at a given temperature, did not make it, as prone to auto ignition as the PRF fuel. For the PRF fuel, the ignition delay came down much more. It's much more, became much more reactive as you increase the pressure for a given temperature. And this is exactly the direction where I was talking about in engines, because what I was saying was, as you increase the pressure for a given temperature in the engine, the gasoline and the real fuels become more resistant to auto ignition. Their octane index is higher because the K value, because K value is negative, they're sensitive, they become more resistant to auto ignition. So this is the main reason why we have this big difference between PRF fuels and real fuels, basically. And the challenge for chemical kinetics is to understand exactly why this is so. Why is the N value different for primary reference fuels compared to non-primary reference fuels? And there is a lot of work being done at the moment, but I don't think it's very clear yet. I mean, exactly what the chemical kinetic reasons for this are. And for engines, in my opinion, this is the most important thing. The response to changing pressure is, of real fuels is very different from that of primary reference. And that's what leads to all the complications that I was talking about in terms of octane index and so on. You know, as I said, this is a very important equation, the Leeuwenhoek-Boole integral, and it is very commonly used to predict knock onset. As I said, when the ignition delay, this integral goes to 1, you assume that you get auto ignition. Because as you can imagine, as it's quite obvious, in an engine, because pressure and temperature are changing with time, this tau is changing with time. So you're never at one point here. So you start maybe somewhere there and come, you know, you follow a different locus there, I mean, basically. So the pressure and temperature, you have to track the whole chain. One approach would be that if you, if you know the pressure and temperature variation with time, you can do a full chemistry, you know, couple the chemistry and actually look at where the heat release occurs. But this is very complicated. But you can also use an ignition delay equation, which is, you know, a function of pressure and temperature, and try to assess this Leeuwenhoek-Boole integral. Right. So, you know, basically, another important thing you have to remember for engine applications is this. At 1500 RPM, by the way, 15 milliseconds is equal to 135 crank angle degrees. Okay? So, a 1 crank angle degree step in the Leeuwenhoek-Boole integral contributes 1 over 135. It's negligible. So, so what this allows you to do is you can ignore, for example, here, you can ignore ignition delays which are more than 15 milliseconds, for instance, because it doesn't matter if you're even spectacularly wrong in predicting the ignition delay beyond that. You know, for engine applications, it doesn't matter very much because it doesn't contribute very much to the. So that is an important point, and I'll come to that in a minute. So this again to emphasize, as pressure is increased for a given temperature, non-paraffinic fuels become more resistant to knock. And this is the same thing as saying K value decreases in this equation, Y equal to, and if you remember, that's how, as T compression 15 decreased, K value decreased. That means as pressure increased for a given temperature, the K value decreased. And that's exactly in line with this kind of observation. You can see here, N-heptane was 1.64. I showed you for isooctane in the previous is 1.5. And all these other things that we have measured for different fuels, gasolines and mixtures of toluene, this is well below 1. So it is very much more, as you increase the pressure, non-paraffinic fuels are more resistant to auto ignition, essentially, right? Okay. So this is making the same point. Now, you know, well, let me just yeah, sensitive fuels have low values of N, so they are, you know, I mean, this is what I just showed you. Now we come to this point I was making about what is the best surrogate for a gasoline. And as I said, if all the empirical evidence shows in all kinds of engines, you know, and knocking conditions in HCCI engines, that if you have the same octane index, that is Ron minus K times sensitivity for a given operating condition, the two fuels will behave the same way in terms of their knock onset or auto ignition onset. So what you want, if you have a fuel with the same Ron and sensitivity, that's the same Ron and MON as your gasoline, it doesn't matter what the K value is. Whatever K value you have, that means whatever operating condition you have, that fuel will behave the same way as your gasoline. So the best a best surrogate is to have a fuel which has the same Ron and MON as your gasoline. Now the simplest one that you can do, which will allow you to do the same, get the same Ron and MON in your gasoline, is a mixture of toluene, isooctane, and N-heptane, toluene and PRF. You could probably do the same thing with ethanol and PRF, or another sensitive fuel and PRF. But we have chosen toluene and PRF. And we have done a lot of experiments, basically. And we, by measuring the Ron and Mon of many different toluene, isooctane, heptane mixtures. And we have, in this paper, established a method to identify what the correct composition is. So if you know the Ron and Mon of your gasoline, you can say so much percentage toluene, so much isooctane, so much N-heptane, will give you the same Ron and Mon as your gasoline. So you now know what the ignition delay is, okay? So we can use that method to specify the surrogate, and you can then do the chemical kinetic calculations for this, and for this PRF, because you can do this, you can't do this for the gasoline, so you can do this for the surrogate and get ignition delay as functions of pressure and temperature, as I showed you, okay? And this allows you to fit a simple Arrhenius type equation with a pressure correction that just I showed you. If you assume, we can ignore ignition delays greater than 15 milliseconds, because as I explained, 15 milliseconds is 135 crank angle degrees at 1500 RPM. It does not matter if you get it spectacularly wrong, beyond that, because it doesn't contribute to the Levengood-Wood integral. So if you are interested not in the real detailed chemistry of what's happening, but you're only interested in predicting knock onset, which is dependent on the Levengood-Wood integral and the ignition delay evolution, you can do this, a lot of simplification like this. So you can use this equation, and I'll go to the next slide. What this allows you to do is simplify your equation for the ignition delay. Because in fact, what you're saying now here is in the ignition delay, we only care about this kind of, this region, basically, where you can fit an Arrhenius type equation, which is like this, So it is a function of pressure and temperature and an N value. So, what you do now is through chemical kinetics now, for any given surrogate fuel, any given toluene, heptane, isooctane mixture, you can calculate this and find what the A value is, the B value is, and N value is. And we have done this for, lots of different surrogate fuels, right? You can further simplify this, because from this table, you can just simply plot, this A, B, and N as functions of some kind of octane index, by the way. This is just empirical fitting of the data. So what you now have is, you can now define an ignition delay. If you know the Ron and Mon of any gasoline that you want to model, you can just use these curves to find what the A, B, and N are, so that you can define an ignition delay as a function of pressure and temperature. But these, of course, these ignition delays are for not for the gasoline, but for the gasoline surrogate. But it doesn't matter, because what we are saying is the surrogate will behave like the gasoline, right? So you have to then validate this thing. You have to make sure that this works. So what we did was, again, we did experiments with many different fuels at 3 operating conditions. And what were the we chose, this is the boosted condition, that means for a given pressure, the temperature is lower, so we are beyond Ron, as it were. And in one condition, we had a higher intake temperature here, with the atmospheric intake pressure, but in this case, we boosted the engine, right? So at these conditions, you run the engine, and you change the ignition timing and so on to get the engine to knock on different fuels. And so you do a spark timing sweep at each operating condition, and you collect pressure data for 300 cycles and so on. And you can, sampling interval is 0.1 cranking angle degrees. And the fuels we tested were these different fuels with different compositions. One contained ethanol, two of them contained 20% ethanol, others were basically gasolines, right, with different RONs and MONs. And this is an example of what happens with spark timing. I mean, in fact, it's what I showed you earlier was before TDC, so they've been flipped across like this. I mean, this is the actual spark timing. And what you find is, as you advance the spark timing, in this case, we measured the fraction of engine cycles of 300, which actually knocked. And what do we call knock? I mean, as I said, it's arbitrary. We just said it knocks if the knock intensity is beyond a certain limit. We just picked a number. I mean, but anyway, what you can see is as you advance the ignition, the number of cycles that knock increase basically, And so this allows, so each of these points now has 300 cycles, and of the 300 cycles here, I mean about 80, in this case, for about 95% of the 300 cycles for this point were knocking, according to us. So we had a lot of knocking cycles, And so how do we then define these parameters, knock onset and knock intensity, etc. Say this is the pressure signal from an individual cycle, one cycle, and you filter it digitally, and you get this kind of signal. And you look at the peak to peak. As I said, that's how we define knock intensity, knock amplitude. And then you say, the crank angle at knock onset, we defined it when this filtered signal deviates from 0 by 0.05. It's again arbitrary. This is what you decide. I mean, and you have to keep on making these kinds of arbitrary judgments or assumptions, in all experiments. There's no choice. So you have to say where you want to say it's knocking. It doesn't matter very much. I mean, the fact that it's 0.05 or 0.1, the difference in crank angles is not very high. And then we say cycles with knock intensity of greater than 0.5 bar were considered to be knocking. And if you remember, I showed you the fraction of cycles that were knocking. That means, in one case I said 95% of the cycles were knocking. That means 95% of the cycles had knock intensity greater than 0.5 bar. I mean, this is our arbitrary definition. Right. So what do we do then? We say, as I said, we use the Leeuwenhoek-Wu integral, and we say knock onset, where knock occurs, starts, is when the ignition, when the Leeuwenhoek-Wu integral reaches unity, and we use this equation. We know A, B, and N for the PRF surrogate, toluene PRF surrogate of the same RON and MON as the various test fuels that we have tested. And we use measured pressure for each cycle, so we don't have any ambiguity about this. We are measuring the pressure in this experiment, right? Now there is another interesting problem. We have to estimate the temperature, and the temperature has to be estimated for the hot spot. Okay, and this is and you just have to make some assumptions here, because there's no way you know what the exact temperature in the hotspot is and how it is evolving with time, because it's a highly stochastic process dominated by turbulent mixing, and you just don't know from cycle to cycle what's happening. But what we do is we make some informed assumptions. So we first of all find the bulk gas temperature, which is easy to do because we can use this equation. We know the pressure. So we anchor the bulk gas temperature at a given crank angle. In this case, we once again use the temperature at when the pressure was 15 bar. We say this is the temperature when P is equal to 15. We know the volume when the pressure is 15 bar in our engine because from the operating conditions we have measured it anyway. And we know the number of moles in the, we estimate the number of moles in the cylinder, fuel, air, and as well as some residuals. That allows us to get the temperature when P is equal to 50. And then we say, actually at that point, there's a hot spot, and the hot spot temperature is higher than the T compression 15 by delta T. We don't know what this delta T is, by the way. You have to make an assumption. We said, okay, for what we found, and I'll show you in a minute, for the two conditions which were not boosted, we could take that delta T was 10 degrees, 10 Kelvin, basically. But when you use the same assumption for the boosted condition, we couldn't get our results. I mean, I'll show you in a minute. It just didn't work out. You have to assume 30 K for the boosted condition. And it's not, I mean, it makes some sense, because what happens in the boosted condition, your 15 bar point occurs earlier in the cycle because your intake pressure is higher. That means when the fresh charge has come in and is mixing with the hot gases, it has not mixed as much, and it's not, so it is sensible to think that this is in the right direction. Instead of 10K, 30K is, I mean, if you had to assume lower than 10K, you would have been worried because it doesn't make as much sense, okay? And then we say, once we know this, so we know so we are using measured pressure at different crank angles, and we just assume that the temperature in the hot spot is just could be predicted by this adiabatic compression, okay? So we know how the temperature is changing with pressure now in the hot spot, right? So we have, this is an example of we picked 5 random cycles in this case. Is it 5 or 4, right? No, yeah, there are 4. Okay, 4 random cycles, okay? And what you find, again, this shows the stochastic nature of engine combustion. Though the operating condition is exactly the same, there are huge differences between the pressure developments. And using the procedure I showed you, this is the hotspot temperature changes. So we know how in each of these cycles the pressure and temperature is changing with crank angle, and so we can calculate the ignition delay now. How the ignition delay is changing with crank angle. This is how it's changing. As the pressure and temperature increases, the ignition delay decreases because it becomes more reactive. And you can see here, I mean, this is the compression stroke before the, and you can see that beyond this point, I mean, our model really is from like 15, milliseconds down. Really, we've ignored everything. But if it doesn't matter if it is, we are very wrong out there, because if you do the Levengood-Wu integral, these translate to something like this, right? So if we are wrong by much here, it will just make a very small difference in our Levengood integral. Then you say these cycles will actually auto-ignite at these crank angles for each. So we can calculate this from the measured pressure, estimated temperature, and our ignition delay equation, right? We can now compare it with the actual measurements for each of these cycles, because we know where auto ignition occurs. And we did this for, as I said, 3 different conditions, 5 different fuels, and in each case we picked, I think in this case, 5 or 10 points, I don't remember now, but we have about 150 points here, I think, in general. And you can see we can predict the knock onset as observed using this kind of model. But remember, we have had to make many assumptions here, and this is inevitable, this is unavoidable. You have to make these assumptions. And one of the dilemmas in this thing is that you don't know whether your assumption about how hotspot temperature evolved is right, or your ignition delay equation, which is based on the chemical kinetic equations that you had, is right. You never know. And we have this other fudge factor. You will never know this, by the way, in reality. But this is very useful. Now we have a validated model, and you can use this model for further studies. I mean, you can see what happens in this engine if we change the pressure, or what happens if we change the RON and MON of the fuel. I mean, where will it, where will knock happen? I mean, that. So knock onset, can be then used, then be predicted. But you have to make all these assumptions. And that's the point I want to emphasize, is that it is impossible to do this without these kinds of assumptions. So we can get a model for ignition delay as a function of pressure and temperature, use the ignition delays from the kinetic model, for TPRF surrogates, and further you can ignore values greater than 15 milliseconds. I mean, again, 15 milliseconds is arbitrary. I just chose this, and 5 fuels of different RON and sensitivity were tested, and using measured pressure. So we have at least eliminated one big problem in this kind of calculations, because it's extremely difficult in spark ignition engine to actually predict how pressure evolves as well, because you have to predict turbulent flame developments, and again, from cycle to cycle, I showed you there is huge variations. I mean, but you have to, at least in this case, we use the measured pressure, okay, and we estimated the temperature, and we predicted Knox onset, by using the Leeuwenhoek-Boole integral, and we get extremely good agreement. So you can predict knock onset. Knock onset is the first thing you can do, but it doesn't tell you what the detailed chemistry is that's happening in between, because we have used the surrogate fuel. Now comes the really interesting point. How do you actually, how do you describe knock intensity, and what are the mechanisms which really determine knock intensity? Okay. Remember, in this case, from the same experiments, we are assuming we set up a threshold value of knock intensity of 0.5 bar, and only what I'm going to show you is only for the boosted condition. I mean, of the 3 operating conditions, we had only the boosted condition I'm going to talk about. Once again, this emphasizes why knock is a stochastic process. These are experimental data. Knock intensity, if you plot it against pressure at knock onset, because we can, in this case, we can, for example, we can get the pressure at knock onset, or the crank angle at knock onset, or the temperature at knock onset, and you can plot the knock intensity against any of these, and there is really no correlation, because it's a really stochastic process. And in fact, if you, for any one condition, if you plot you do the probability distribution of knock intensity, you find this kind of log normal distribution. Other people have also seen this. Basically, it's not pure. I mean, perfectly log normal, but that's the best description of it. What this means is there can be some very high intensity events. The engine was operating in exactly the same condition, but because of cycle to cycle variation, we are getting huge variations in knock intensity, okay? And it doesn't, even for the same operating condition, fuel, spark timing, the phasing and pressure at knock onset varies. I mean, because you have this variation. And this variation comes about because of cycle to cycle variation, which originates because of turbulent flame development problem. I mean, that it is, it's not, it's stochastic. So for the same pressure and phasing at knock onset, so if you just draw a vertical line here, there are big variations in knock intensity, okay? But so just as I showed you, Leeuwenhoek-Boole and kinetic models that I just described enable us to predict the knock onset, where knock is occurring, but it doesn't tell us anything about knock intensity. Because knock intensity, for example, depends on how the pressure wave set off by the initial auto ignition travels through the hotspot, and how the pressure wave evolves. I'll come back to that. Now, if you plot knock intensity and other parameters at knock onset, like crank angle, pressure at knock onset, ignition delay at knock onset, temperature at knock onset, there is a mess. I mean, in sense, there's no correlation, basically. There's a huge variation. And we can understand this within this theoretical framework. Derek Bradley from Leeds and co-workers have basically shown that the most important parameter which determines knock intensity is this velocity of the auto ignition front. Because what happens is when auto ignition occurs, it sets off a front a wave, auto ignition wave, which starts traveling through the gas. And how fast it travels is the critical parameter. In particular, they defined what they call a resonance parameter, which is the ratio of the speed of sound and this velocity of the auto ignition front. And the speed of acoustic velocity is given by square root of gamma RT. And in a paper that Derek and I did, we showed that it is approximately, you can write that delta Pmax, the maximum pressure amplitude of the knock signal or the pressure fluctuation signal divided by P can be approximated by 1 over psi square, 1 over psi square. I mean, this is, I won't go into the details of the model. Now, the way we are defined knock intensity means delta Pmax is equal to knock intensity divided by 2. We know the ignition delay. This is the ignition delay equation we have used. And therefore, you can, by using this equation d tau I by dt, we can define UA like this. And knock intensity now, combining all this, can be defined as some function of only pressure in this case, because because temperature is dependent on pressure, the way we defined it. Where Z is this, this equation, and this dx by dt is the 1 over dt by dx is the temperature gradient in the hotspot. We don't know this, by the way. Okay, we have no way of knowing this, but this is the equation now, and we have a lot of experimental data that I showed you, and we need to now convert this using this equation, how this gradient of temperature is changing. Right. So for the various, for the 5 different fuels, if you plot Z, this Z value which I showed you, against the pressure at knock inset, you get different lines here. I mean, and in fact, this fuel, the blue one is the highest Ron fuel we have got, yes, and this is the lowest Ron fuel we have had. And if you plot the and because we measure knock intensity for each of these points here, we know the knock intensity, we know the pressure at knock onset, we can calculate this, and we can get dx by dt for each knock event that we have measured. And if you plot dx by dt against z, this is what you get. So one of the things that you see is for the same knock onset pressure, the higher octane fuel, this one has a lower value of Z, right? And for the same dx by dt, therefore, it will have a lower knock intensity as well. And of course, it will have, in other words, it's more knock resistant. We can think about it this way. But this framework, model framework, also shows this, by the way. And why? So even if you plot dx by dt and z, you can see for the same z, you can have many different values of dx by dt. This is a variation. Because, and once again, knock is a stochastic process. You can have very different values all these parameters for each condition. So if you combine a high value of z and a high value of dx by dt, you will get very high knock intensity, basically. That's what it's telling you, really, right? So this is what, because all of these things can vary from cycle to cycle, you will get this big variation knock intensity as well. Right. So this is the point. High value of z alone or dx by dt alone does not necessarily lead to a very high intensity knock. This can result if these two are paired with each other at high values. For example, where is the point A? I don't know. I mean, I think it's one of these points here. There seems to be, yeah, anyway, this is the main message, okay? And now, we have a lot of data about this dx by dt, which we have, extracted from all these experimental results. And if you plot this against crank angle, you get this cloud, basically. And for each condition, if you, in fact, if you combine all this data and you define, you can find a distribution curve. That means, again, it's stochastic, it's probabilistic. Dx by dt is not the same every cycle. There's a most probable dx by dt value here, And this turns out, in this experiment, that it's about 0.44 millimeters per Kelvin. That is dt by dx, that's temperature gradient in the hotspot. The most likely value for this is 2.2 Kelvin per millimeter in these experiments. That's what the experimental results are telling us, right? And it so happens that this is the, okay, now let me come to, again, what you find is, okay, I won't go into this because it's a bit complicated. By using these, you remember I told you that we make measurements in 3 different operating conditions. One was the boosted condition, and the other 2 were non-boosted conditions. And that allows you to go to different areas of the crank angle and pressure at which knock occurred. And essentially that allows you to calculate these for each condition how, this, estimate how this temperature gradient changes. And it makes sense, okay? Anyway, let's leave that, and now I'll come to super knock. Super knock is something, as I explained to you, even if you have chosen operating conditions where you're completely avoiding knock, suddenly you'll get some cycle like this, okay? And this is a very, very big problem now. As people are trying to downsize and boost the engines, this is becoming the main barrier to further downsizing and so on, because it's unpredictable. But within this framework, we can understand, we can set up a theoretical framework under which we can understand this. And what is super knock? We basically say it's a very violent knock event. For example, in this case, the peak-to-peak knock intensity was 140 bar. If you remember, I said our threshold value is 0.5 bar. So it's 280 times worse, basically, And again, Derek Bradley and co-workers have developed this framework, and they ascribed it to what we call developing detonations. And this is based on work that Oppenheim and Zeldovich and the big giants of combustion theory, they did this many, many years ago. And they have developed it further. And what essentially it boils down to is, you remember we have this psi value, which is A by UA. And they also define a reactivity parameter, which is called, which is R naught over A by tau E. What R naught is the radius of the hotspot, which we don't know, by the way. It's just the radius of the hotspot. And tau E is like the ignition delay time, but it's the excitation time during which most of the energy following auto ignition is dumped into the system. So it is a much shorter time delay, I mean, compared to ignition delay. Ignition delay, remember, is what happens up to, when you have a pressure and temperature at a fixed condition. If you put the gas there, how long does it take before it starts, it auto-ignites? Tau E is what happens after it auto-ignites, how quickly it dumps the result. So essentially, what you find, what they found is that you can plot this, you can find a peninsula here where developing detonation is much more likely. This is from DNS and theoretical calculations. It's a very complicated calculations that you have to do. All this area is not of much interest in spark ignition engines. This is much more interesting for explosions and large-scale, developing detonation, which can be extremely destructive. It can destroy, what might happen when you just set off a bomb, for example? That kind of thing. Well, actually, that's not quite the right analogy, but in the sense, these are very important areas when you try to describe explosions and developing detonation. But in our engine, if you take these 3 cycles, we can calculate psi, epsilon and psi with some assumptions. We assumed, before we did all these other experiments that I talked about, we assumed what R naught should be. And in fact, in order to do that, if you go back, you have to assume a value for the temperature gradient in the hotspot. We just happened to assume that it was 2 degrees per millimeter, and I just showed you the data from the experiments. It came out at 2.2 degrees per millimeter as the most likely value. It was just luck that we had chosen that. So you have to fix that, and you have to choose a value. I think we chose 5 millimeters as R naught, and we can make an estimate of this as well. When you do that, what you find is for these 3 cycles, this cycle is well out of the developing detonation. This is what you might call a normal knock cycle, because the pressure, etc., are not high enough. But whereas this cycle is well into the developing detonation, and this cycle is in between. Okay? So what this is telling you is the very high knock intensity is consistent with this fact that it is a developing detonation. So remember, we have knock onset, which is determined by ignition delay and chemical kinetics and how the ignition delay evolves with temperature and pressure. And the knock intensity is what happens after the auto ignition occurs, and that depends on how this wave of auto ignition has traveled and interacted with the temperature gradient. Right, and what we can do now is look at some whether this model allows us to come to some kind of useful conclusions. For example, what we find is that what I've plotted here is coming back here. So we can say we set this psi of at 5 as our threshold value for developing detonation. What we say is if this psi value is less than 5, there's a good chance that we get developing detonation and super knock, right? So let's see what happens now. What we have plotted here is for different fuels, ethanol, MTB, and various other fuels, you can calculate these things. Because this is the equation for psi, and we make an assumption of for delta. We know the dx by dt is of 0.44. We put that assumption, and you plot this, and this is our threshold value. And what you find here is something like toluene. If you want to push it to developing detonation, you have to increase the pressure at knock onset to extremely high pressures. Whereas this fuel, which is the 92 Ron fuel, if you push, if autoignition occurs or if knock occurs at about 80 bar, it's a good chance that you will get developing detonation. Okay? So this allows us to understand, how fuel parameters actually affect this possibility of developing detonation. And I mean, the big point now is, why does it occur in the first place? Because you've taken all your all these precautions not to avoid knock in the first place. And this actually possibility of developing the high pressures and developing detonation occurs because of an entirely different stochastic phenomena, which is pre-ignition. Because pre-ignition sets off the flame before the spark actually fires, and that increases the pressure in the cylinder, and that could give you this, leave you to this condition basically. Now, what is pre-ignition? Pre-ignition is basically establishes such stable flame before the spark plug fires, and again there is fundamental combustion theory from going back many years, which shows that the criteria for successful flame initiation are that there's an ignition criterion, which means the local temperature should increase sufficiently that you start chemical, reaction, a runaway chemical reaction. But that is not sufficient. There is an initiation criterion which requires that the initial flame that you get from this ignition, it must reach a critical radius before it becomes self-sustaining. But if it is smaller than that, it will just collapse and die. I mean, this is the same idea that, I don't know if any of you have done combustion theory in here, but same idea of, that, about quench distances and so on. Basically, if it's smaller than RF, it will just collapse and die. Okay? Now, how can we get this initial ignition? How can we get this hot spot to begin with? This is, remember, during the compression stroke when there is no, the pressures and temperatures are low. And what you can show beyond doubt is that it cannot be because the autoignition of fuel and air mixture. We have been talking about autoignition and knock in fuel and air. And if you use the Levengood-Wu integral, it will simply not go to 1 anywhere near during the compression stroke. So it can't be because of fuel and air autoignition. Okay? In modern boosted DIS engines, it seems to originate away from the surfaces. In the past, it used to be hot spots on the combustion chamber, etc. And it looks like droplets of fuel and lubricant somehow undergo some kind of chemical reactions, chemical kinetic and catalytic reactions, and they form this hot spot in the during the compression stroke. And this is not too fanciful, because lubricant is much more prone to autoignition than fuel. I mean, it is much worse than N-heptane. So it is possible that it will autoignite like that. Basically, all these things become much more possible if the pressures are high. I mean, this is exactly what you find in reality. This pre-ignition and superknock only occur in boosted engines. If you reduce the pressure, this just goes away, basically. So, so it is all consistent with the theory. And in fact, you can go a little bit more into the detail, and what you find is, well, I won't go into the detail actually here, because the criteria for basically what it requires is that this critical diameter is of the order of the laminar flame thickness. I mean, this is again from fundamental combustion theory. I mean, it is again related to things like quench distances and so on. And you can write the laminar flame thickness as basically, where D is the thermal diffusivity, which is related to dynamic viscosity and density, and laminar flame speed. Okay? And if you combine all of these together, and we can look at how pressure and temperature are changing, etc. Combine all of these together, you get an equation for delta, which is the laminar flame thickness, as functions of pressure, temperature, and laminar flame velocity. And essentially what the theory says, if this laminar flame thickness is small, and that for a given temperature and pressure, it will be small if the laminar burning velocity is large, you are much more likely to get a flame development, pre-ignition. Because the whole idea is, remember, completely probabilistically, stochastically, you will get these hot spots. And the chances of finding a hot spot which is large enough to set off a flame obviously increases if delta is small, because that's the criterion, that the initial flame should be, the hot spot should be, larger than delta. So in fact, what you find is, actually this explains a lot of experimental observations. What you find is fuels like hydrogen and ethanol, which have high laminar burning velocity, are bad for pre-ignition experimentally. That's what happens. And if you increase pressure, because this Y is usually 0.2, if you increase pressure, you reduce delta, and that's exactly what happens. If you increase pressure, pre-ignition becomes much more likely. So there are lots of observations which fit in with this theory. And in fact, you can plot this pre-ignition propensity, which is, again, I won't go into the detail, but for many of these fuels, Ricardo actually had a test procedure, and he assigned, just like Ron and Mon, he assigned a pre-ignition resistance to different fuels, and for which we know many of these fuels, we know the laminar burning velocity as well. And if you plot this, there is a good correlation as predicted by this. So essentially what this is saying is pre-ignition can occur randomly because of these hotspots happening, and it is for all other, if all the other conditions are equal, a fuel with high laminar burning velocity is more likely to give you pre-ignition. If you increase the pressure in the cylinder, you're more likely to get pre-ignition. And then what you find, I mean, of course, I'm making this point again and again, this knock is a stochastic process, occurs in hotspots, should really be described in probabilistic terms. But knock onset can be predicted by using limit-Goodwin integral under many assumptions that I talked about, But knock intensity, depends on this psi, and and it can be related to this parameter z, which depends only on pressure using our simple model, and at knock onset, and the square of the inverse gradient of temperature in the hotspot. We don't know any of these. I showed you some from experimental results. We got a lot of data. We estimated a lot of these parameters. And for a given fuel and operating condition, this varies because pressure varies, because cyclic variation, which is again a stochastic process because of turbulent flame development. And Z increases, and the probability of high knock intensity increases as P increases, pressure increases. Okay? For example, by boosting the engine, using turbocharged engines. And for a given pressure, Z is lower for a fuel with more auto-ignition resistance. That the higher Ron fuels are less likely to give you developing detonation. But this depends on the evolution of the hotspot, and that's a stochastic process. We can't really determine it, we have to describe it probabilistically. And superknock is caused by developing detonation, which results when the value of psi is so high, that you get developing detonation. I didn't describe what developing detonation is, but let's leave it at that. Engine operating, this is an important point to avoid knock and auto-ignition fuel-air mixture. Hence, they are very far away from conditions required for superknock. Nevertheless, superknock occurs. Why does it occur? It occurs because of pre-ignition, which is yet another stochastic process, which is completely different from auto-ignition and developing detonation and so on. And and this we know for this to pre-ignition to occur, the local temperature has to increase beyond a critical value, and this cannot be because this we can be certain of. So pre-ignition does not depend on RON and MON, which are auto-ignition characteristics of fuel. And there's another initiation criteria has to be satisfied. So if all else is equal, the chances of pre-ignition increase as laminar burning velocity increases. That means fuels like hydrogen and ethanol are bad. And all else being equal, the probability of supernoc decreases as fuel RON is increased because the Z value is decreasing. Okay? And increased pressure increases the probability of both supernoc and pre-ignition. However, with the high RON and high knock intensity and high knock intensity and supernoc can occur with the right combination of Z. And so basically, it is a stochastic process. There is a whole chain of probabilities involved. Firstly, you have to form the hotspot. That should set off the flame. That's a stochastic process, and that should then cause auto-ignition in your end gas, and that should happen at a high enough pressure that you can get developing detonation. And then when all these probabilities come together, you get supernoc. And this is why it is very rare. I mean, 1 in 15,000 cycles or something you observe. But as you increase the pressure, these occurrences will increase basically, and that's what the model helps us to understand. But it is a stochastic process, so you have to describe what the probabilities are. The probabilities increase as these other various things increase. So that's where I'll stop. I mean, so it's 4:15, so we need to, yeah. So any questions?